Welcome to another lecture on quantum computing. We are in a good position now. We know what are different parts of a quantum circuit, right? We know the input state is a vector. We can apply unitary operators to it. Those are our gates. For example, poly XYZ, C0, Hadamard, so on and so forth. And then we measure. The measurements which we will mostly use are the standard basis measurements. That means if the state is alpha 0 plus beta 1, I will measure 0 with probability mod alpha square. I will measure 1 with probability mod beta square. Right? So this is what we understand about measurement, and then slight subtleties which we have to keep in mind. The difference between classical and quantum we did last time. You will remember that even though in classical circuit you can keep making copies of your output and use them in as many different gates as possible, that's not allowed in quantum, because quantum has no cloning theorem or no copying principle, right? Again, the workspace. So I should write ancilla as workspace. In the classical computation, if I use some extra register to do intermediate calculation, I do not care about the state of this extra register once I finish the use of it. I kind of throw it away. But because of entanglement, it's kind of important that in a quantum circuit, I keep track of whatever registers I have used throughout the calculation. And if I'm sure that I have restored them back to their original state, then I can keep them aside. But in general, we will keep track of all of the registers. Obviously, to make a sensible classical hardware, we need to tell the hardware designers, give us these gates. We can't tell them that, give me all possible gates, because those are a lot. So then there is a concept of universal set of gates in classical computing. For example, AND and NOT, for example, AND or NOT, for example, just NAND. Similarly, there are examples of universal gate sets in quantum. The slight difference being that using the universal gate sets, now you can approximate any unitary. Instead of saying that you can exactly calculate any unitary, you can just approximate it. Okay, and because you can go easily from one universal gate set to another, you can assume that you have access to almost all kind of known quantum gates like polys, Hadamard, C0, 1 qubit gates, because all of them you can go from each other in constant. Okay. And this idea of uniformity, that when you actually create algorithms for a problem, which has input size varying from 1, 2, 3 up to n, the quantum circuit you make should have some pattern. It cannot be that your circuit for input size 1 is very, very different, has no relation to circuit size for input 2, circuit for input size 3, and so on. This condition is called uniformity, and it's mostly that's how you will create quantum circuits. But we have to remember that ideally a quantum circuit should follow uniformity, and without much effort from your side, it will. You will see that. Sounds good? Okay. So today's class is going to be fun. We are going to play with circuits a lot. But before that, I wanted to tell you about principle of deferred measurement. Right? This I have talked about before. I said that in a circuit, you can assume that all measurements are done at the end. Why was this theorem, or why would this rule be helpful to us? If we can say that, all measurements I can push to the end. So, okay, remember, we start with input. What kind of things we can do with quantum states? We can measure, or we can apply some unitary operator. And in general, nobody stops us from interleaving them, right? You measure, then you apply some unitary, then you measure again, then you apply some unitary. You can do all those kind of things. So a general quantum circuit would actually look like interleaving of these unitaries and measurements. But I am saying we can simplify our life. We can always assume that you do all the unitaries first and you can do all the measurements in the end. Why is that good for us? It doesn't really save computation in the sense of the computer, but it saves computation for us, for our analysis, right? Because as you measure, then suddenly you have two cases opened up. If it was just 1 qubit, if it was 10 qubits, you will have to do the power 10 cases opened up. And now for each of the case, you'll have to write your state calculations differently. Okay, so if I can push measurements to the end, my life becomes simpler. Actually, other way also, it's useful in the sense that if I measure in the end, then I have to keep all the qubits alive all the time. But the current hardwares, the number of qubits are restricted. So if I can push measurements before, then I can make work with less number of qubits sometimes. So just for the systems where number of qubits are limited, it is possible, it might be possible some circuits that I push measurements in the beginning, I calculate the answer and then use those qubits once more. Right? So then it could actually do the computation with less number of qubits. So this idea of moving measurements here and there is very, very useful for us. Don't worry if you don't understand the proof of it, but you should remember that you can do it. And what are the subtleties? So let me point out the subtleties. I said I can move measurements to the end. Seems like these are the two circuits where I have moved this measurement in the end. Notice two measurements together makes just one measurement. So then whatever I said, if you take the direct picture of it, then these two circuits should be equivalent. Are these two circuits equivalent? How would you prove that such a circuit is equivalent, not equivalent? So you should create an input state so that the output is different in the two cases. Correct? And what would be your first guess for the input state? Sorry? Just take 0. Just start with 0. If it doesn't work, then we will go to alpha 0 plus beta 1. Okay, so let's start with 0. What will happen here? You apply header mode to 0, then apply header mode again. What state will you get here? Clear, right? Header mode is its own inverse. So here, I am always measuring 0. Correct? What happens here? You apply header mode, you have plus state. Now, I am in two cases. With half the probability, I am in 0. With half the probability, I am in 1. If I am in 0, this will change to minus. 1 will change to minus. Everyone is following, right? And in both these cases, I will measure 0 with half probability, 1 with half probability. Right? So the statistics I obtain here is very much different from the statistics I obtain here. I will never obtain 1 here. Here I will obtain 1 with half probability. Right? So clearly these two circuits are not equivalent. So the punchline is okay, yes, you can move measurements, but you have to be careful. It's not as simple as, just take the measurement and push it in the end. Okay, so how do you do it? Let's say you have some unitary U, and let's say I measure everything. I don't need to, but let's say I measure everything. Then I apply U prime. I don't want these measurements. I want to push them to the end. Correct? The way to do it is I move this using ancilla downwards. What do I mean by that? The equivalent circuit what I'm going to do is tell you an intuition of why this works. Okay? You will remember that principle of deferred measurement is true with the subtlety. If you are interested in the proof, there is a reference. You can try it first. You can actually do it by yourself. If not, there is a reference given in the notes where you can see the proof. But these two circuits are equivalent in the sense that the statistics obtained here and the statistics obtained here are going to be exactly the same. Okay, and now I'm going to describe you the intuition of why this works. Clear? Questions? Okay, so you will see the intuition. If you want to see the proof in detail, try it first. Otherwise, there is a reference. What is important is you remember this principle, that using ancilla, we can move the measurements to the end. So for our quantum circuits, we will always assume that we are doing measurements at the end. Good. Any idea why are these two circuits equivalent? What have I done here? I move on. Oh, sorry, I should have said that. That's important. I start with zeros and do this. What I will do is, I will take a very simple U and then we will see how that works, right? Because anytime there is a complicated thing, examples help, right? So let's take an example. Let's take a very simple circuit. Okay, so yeah. Right? So this is just for intuition. I will explain how that circuit is working after this. Okay. So how will you analyze this circuit? You will say, oh, after this circuit, I have half probability of being in 0, half probability of being in 1. So then I will start with case 1, measured 0, case 2, measured 1. Correct? And then I will say, oh, if I measured 0, this will stay 0. If I measured 1, this will flip to 1. Correct? And then let's say, measure here, I measure here. Correct? What happens in this circuit? I start with a state times 0. Okay. When I apply the C0, I get this state, right? By C0, what I have done is, I have actually copied the measurement output in this state. I had two cases here, measured 0, measured 1. So instead of making the case, now the second qubit will tell me whether I am in case 1 or case 2. Okay, and you will see that the exact same thing happens with half the probability I am going to measure 0, with half the probability I am going to measure 1. Right? If this state, if I measure my first qubit or a second qubit, I will measure 0 with probability half, I will measure 1 with probability half. So it's the exact same statistics as this case. In these two, both have two qubits. Right? Number, right? So in general and for simple circuits, I have one qubit for one line As we move up, it will change. But at this point, one line represents 1 qubit. Right? This is not going to be true in the entire course. At this point, I am representing 1 qubit with 1 gate.
So in the first circuit, after we do the C0 operation,
yes,
both the lines are actually entangled, right?
Yes. Yes.
So irrespective of whether we measure on the upper line or the lower line, we get the same answer.
Same.
Whereas that would not be that would also be the case in the second one, where we are not measuring something with the upper line and then we are measuring it in the
See, this is a classical bit now, so there is no point measuring this. But it will be correlated to what you measure here. Right? So the exact measurement, so if you want, you can put a measurement here. This is a, I don't know, this is a classical measurement. The point is, the correlation will exactly stay. And what I'm saying is, this is not very surprising, because by C0, what I have done is I have just moved this case 1 and case 2 as second qubit. Okay, and this is the same thing which is happening here. Okay, what you can see is that suppose the state here so suppose there were some k qubits here. Okay, now one line is not representing 1 qubit. Suppose there were some k qubits. That means my state will look like this. K qubits means my basis states are strings of length k, correct? So it looks like this. This is on. K qubits, correct? So I have this state. When you apply C0, what you are doing is you are changing the state to, and this is something which you can verify. This. Notice we are not copying the entire quantum state. This state is not equal to we have not copied the entire state. This we have seen last time also. What we have done is we have in some sense copied the measurement if we had measured it. If I had measured it here, if I had obtained Z, that now goes in my second qubit. And if I don't do with my second qubit, all these computations will run in different cases. So this is a nice way to keep track of different cases. And that's why your final statistics will not be different. As you measure this, so this, when you measure Z, this will correspond to case Z. Right? If you had analyzed this, you would say, oh, if I measure Z, that is case Z. Correct? Now here, all the computations will be happening here, and then this will correspond to case Z. Again, I'm only giving you an intuition. This is not a proof. You can try the proof, you can see it in the notes.
I got the point. But
C0 is kind of measuring the copying the measurement outcome.
But I'm confused that what is the problem if we put measurements earlier, like
There is no problem. A general circuit would look like this. But then I will have to analyze the state in terms of probabilities. Case 1, case 2, it's just more cumbersome to keep those cases alive. Instead, it's just easier to say, oh, my state is this, my state is this, final state is this, and then measurement happens in that.
So if we use this kind of circuit to represent anything, then we have to go probability by probability. These might happen, these might happen.
Yes, this allows us to keep track of those probabilities just in one state. So it's a mathematical convenience. It's not anything different. That's what I'm trying to emphasize. But it becomes mathematically convenient to analyze things. So that's why we will change this circuit to this circuit. Right? So this is not fundamentally better or anything. Yes, Dinesh.
In this case, if we measure state states,
Hmm.
so what will be the measure? Like, because after C0, the quantum state is entangled.
Oh, this one, yes.
After 0 is
Yes. So if you measure both, with half the probability you will get 0, 0, with half the probability you will get 1, 1. Here, no, it will exactly be the same. Case 1, if it is 0, then this state is 0. So you are measuring 0, 0 with half the probability, case 1. If here the state was 1, if you had measured 1 here, then this remains 1, this becomes 1. So you measure 1, 1 with half the probability. So don't look at the state. The statistics you obtain here is exactly the same, which is with half the probability you get 0, 0, with half the probability you get 1, 1. Oh, you mean this here, this? Try it and see. It won't work for some cases. It might work for this case, but in general it won't work. You can try. Okay. Yes. It depends on the kind of an algorithm designer. At this point, we are telling algorithms what he or she can do. We have said you have two weapons of choice, two weapons of mass destruction. One is unitary, other is measurement. And then if you give two weapons of mass destruction to a classical person, you say use AND gate, use OR gate. You won't say use OR only in the end. You will say, oh, how much times you want to use AND, how much time you want OR. So in general, a very intelligent algorithm designer might say, oh, I do unitary, then I do measurements, then I unitary, then measurement, I can do that. What I'm telling that intelligent algorithm designer is, by making slight changes, he can just push his measurements in the end. So I'm not saying that I need it now, but in general, as a recipe of an algorithm, it is possible that some algorithm needs this interleaving. What I'm saying is that interleaving can be converted into unitaries first and measurements later by a small trick. And that small trick is applying COT. Why does that trick work? Because essentially I have copied my output to the second register, and this will keep track of my keys set. Okay? Am I questions? So again, what you need to remember is principle of deferred measurement, which says you can push measurements in the end using NCEL. If you want to see the entire proof, you have the literature. Okay, and if you are a person who likes linear algebra a lot, actually I had talked about density matrix representation. Remember, I did not talk about it, I just said that this is a way to keep track of probabilities. The density matrix representation of this is this, like this. Okay, it just converts this tensor product into outer product. And I think you mentioned one time that, oh, it's just converting a rectangle into an array, right? So that equivalence is actually helpful. That's how we actually, in the real world, we would say that we will just keep a density matrix and we don't have to keep NCEL bits. We can keep track of everything using density matrix too. Okay, and that is using the fact that tensor product can be written like outer product. Okay, so, but yeah, this is for people who kind of worry about this thing. Message is, we can keep measurements in the end and still be happy using some NCEL bits. Okay, good. So if now you are ready, then you have to solve a lot of questions. Are you ready? Pen and paper? Okay, let's see how to add two numbers using a quantum circuit. And since we are computer scientists, these two numbers are given in binary. What is the addition of these two numbers? Binary. Can everyone do it? Go ahead. So you do it exactly the same way as you would add in base 10, just that you will remember 1 plus 1 is 10. What it means is 1, 0, 1 plus 0 is 1 plus 1 is 1, 0. That means 0 come here, I carry 1. Right? And if you understand addition base 10, it's very obvious why you are doing it. You are basically transferring 2 into the next digit. Now 1 plus 1 is again 10. Okay, if you want to verify, what is this number? What is this number? 8, 2, 1. Right? So this, everyone is fine now, right? Create a quantum circuit to add two binary numbers. Create a quantum circuit to add two binary numbers. Remember, this is just a classical problem. Your input is classical. I will always give you input to be classical. Your output is also going to be classical, but just to torture you, I want you to make a quantum circuit for it. Okay. If you see this, if I break it down into parts, essentially I will say that what I am interested first is in creating this half adder. What half adder does is it takes 2 bits, correct? It calculates the answer and the carry. Make sense? This is the basic subroutine which I am using again and again. Can I at least create a quantum circuit for this basic subroutine? So what is this basic subroutine doing? If I give it 0, 0, what answer should I get? What carry should I get? If I get it 0, 1, what answer should I get? Sounds good? Okay. It's not a very difficult but a non-trivial problem to use this half adder and create the full addition. That we will do later. Let's see if it can at least do this. So what is the first observation? You want a circuit which takes 2 qubits like this and answers 2 qubits like this. What should be your first observation, suggestion, complaint? Sorry? It is on the basis, but then it also tells you one more thing which is more important. Keep looking. So, what 2 qubit unitary will go from here to here? This is what I want, right? I have 2 qubits given here. I want to generate this 2 qubits. What 2 qubit unitary will take me from here to here? That's the question I am asking. Again, before answering, did you check? I'm sure you did not, because you know the action of C0. You thought, sir ने C0 ही तो पढ़ाया है यार, और क्या होगा? Probably it was Hadamard times C0. I mean Hadamard tensored identity multiplied by C0. But you have to. So let me help you out once again, because I am a nice guy. It's a trick question. Now can you tell me the answer? Very good. There is no unitary like this which can go from here to here. Why? You can do it again. Remember unitary definitions. This is the basis. Is this a basis? What is the net product between these two? 1. What is the net product between these two? It is not taking an orthonormal basis to orthonormal basis. It is not reversible. if I tell you that my output is 1, 0, there is no way you can tell me what was my input. So there is no quantum circuit in the world which can just take 2 qubits, go from here to here. You should know this. This is the first step, right? Always. Okay. And there's a general trick for this. So what we will do is our half adder is actually going to take two ancilla bits. Let's say, I wouldn't say AB. It's going to calculate answer and carry in the 2 ancilla bits. Okay. And clearly, if I have AB, I know all these 4 numbers. If I know all these 4 numbers, I know AB. Right? So this is definitely reversible. It's not clear what reversible is. What should reversible mean? Reversible means, given the input, there is a one-to-one mapping between input and output. Knowing the input, I know the output. Knowing the output, I know the input. So in this case, if I know my input is AB00, there's a unique output here for no they can map to same 4 numbers, obviously, because if A, B and A prime, B prime are different, first 2 qubits will be different, leave alone the other 2. Right? And knowing these, I can come up with these. Yes. We can use 3, but the reason I'm using 4 is because in general, this is the technique that what will happen is in future, you want to compute some classical function. You have some input qubits. Now your output might be 1 bit or 2 bits or whatever. What you do is you calculate your output here. So this is a standard way in which you can make the classical circuit reversible. So the intuition is coming from here. We know that whatever classical circuit you can make an equivalent reversible classical circuit. Okay, this is without quantum, these things are known. And the way to do it is to convert your classical gate into a gate like this. This is exactly what I am doing. I have written answer carry, but what it will do is do this. So any classical output I want to compute, I just compute it in ancilla as XOR. And using this trick, now you can replace every classical gate by the reversible gate. Your entire calculation becomes reversible. So in this special case, if I really want it to be reversible, you are completely right. I can do it with 3 qubits. But I want to follow this general recipe. That's why I am doing this. Make sense? And since you mentioned it, you have got into your trouble, make a 3 qubit reversible circuit and create a half adder. You can. Okay, it's actually easier. See, this is a very important point about research. When you ask such questions, that's when your understanding develops, right? Why did we jump from 2 to 4? Why not 3? What can I do with 3? What can I not do with 3? Right? So these questions are good to ask, right? Okay, great. So now I have this circuit. How will I calculate answer now? Right? Now my problem is simpler. If my input is 0, 0, I want to get 0. If my output is 0, 1, I want to get 1, 1, 0, 1, 1, 1, 0. So it is in some sense XOR, right? It is actually XOR. If I did not want to calculate here, sorry, what is this square? C0. This is exactly C0. This is the reason why you write a plus here. You can check that. notice when I write this, A and B are classical bits. This is not for quantum. This I am writing, when I write this description, A and B are classical bits. Because if A and B are quantum, I don't know what this operation means anyway. But using this, I can make a meaning of what happens if these two are quantum things. But I don't care. In this case, I want to add just two classical things. Right? So, do you agree with this? You can check. If A is 0, B is 0, you will get 0, 0 XOR 0. You can check all four. This will be fine. The only point is, I don't want this. I want this. What can I do? Because I want to calculate in the ancilla, right? I don't want to calculate in the... Try it. You have pen and paper. Sometimes just trying different things work. And it's not difficult. Actually you can logically figure out what to do. Knowing this, you can. Exactly. Very nice. First C0 will make the XOR with other will make the XOR with B. Not 0, B. What happens here? This is what C0 does. What happens here? Great. So there is a very, very simple circuit which calculates the answer. Now what about carry? Very good. We have seen this. What is carry doing? It is saying, give me 1 only if we both are 1. This is the AND gate. And we saw how to execute AND gate previously, classically, right? So this carry is basically right. So what is the half adder circuit? There's a simple use. In some sense, we are saying that most of these classical gates we can simulate using quantum gates, right? What did I do? I could simulate AND using CC0, correct? How can I simulate NOT operation? Poly XOR C0, correct? That's what. So if you want direct NOT, you can use X gate. If you want controlled NOT or like NOT in this way, you can use C0. So now you can do NOT operation, you can do AND operation. NOT comma AND is universal for classical gates. That means you take any circuit, write it in terms of AND and NOT, you can convert it into a quantum circuit, which has C0 and CC0. And actually you can even convert C0 into using CC0. You can always give a 1 for the first, right? So everything you can do using CC naught. Okay, again, I'm not giving you a complete proof. It is, you are computing like this, you have to keep track of these bits, but you can do it. It's the idea is that you can, every gate, you can make it reversible, and then you can use those reversible versions to convert all classical circuits into quantum circuits. Okay. But now I have half adder. I did not want half adder. I wanted full adder. That you will do. This is just good fun exercise. So you want to add A0, A1. Okay, I shouldn't write it this way. You have a number A, you have a number B, you want to add and give the output. You can take half adder as the black box. Okay. Also, I will make your life easy. You don't have to write 4 inputs and 4 outputs. Okay. We will just, the A, B's we can ignore. So you can say that answer carry. Okay. Actually, there will be 2 here, but you will only be using these. That's why you don't have to draw these extra wires. Remember, this is all classical computation. These wires are not entangled. That's why I am not worrying about these extra wires. Okay, so go ahead. You have a half adder box. We know how we have constructed the half adder box. Using this, make a full adder. Of which the first half adder will be applied to so A1 is the more significant bit, right? Your number is A1, A0, right? A1 is the more significant bit, A0 is the least significant bit. That's how I'm ordering it, right? So for example, if A is 2, then A1 is 1 and A0 is 0, right? How do you represent 2 in decimal, in binary? 1, 0, right? So 1 is the more significant bit, 0 is the least significant bit. Try. I told you, start with A0, B0, right? Definitely you want to add A0, B0. Then what do? So the answer did not going to happen. Think about it. This is already your first bit of the answer, no? So there is no half adder attached to this answer. This goes as the first bit of right answer. This is answer 0 or something. You need 3 bits, answer 0, answer 1, answer 2. So answer 0 is gone. Now you take this carry and use something else, again half adder. You don't have to worry about this. You can just make using boxes, right? So A0, B0 box.
So, yeah, there must be at least 4 inputs, right? A0, A1, B0.
Those are the 4 inputs. A1, A0, B0, B1.
Like suppose D0 and D1 and then whatever.
D2.
D2, that will be the output.
Sure. So is this something? Does it represent something? Does it not represent something in your answer? These 3 are there. What can you do with these? In some sense, you have to add these 3, right? And one of them will go as the answer second bit. So what is, so carry you are giving it to, okay, good, okay. Sorry, yeah, yes. Why should it be different? So, but what I'm saying is, that's a very basic, simple problem which you can solve. Correct. Now, what you know is, if all these 3 are 1, then my answer 2 is 1. Correct? Now the carry here cannot be used here, right? The carry here is what is the coefficient of 4 to 2 square now, right? A1 was, if you look at this number, this is 2A1 plus A0. This is 2B1 plus B0, right? So this bit is actually multiplying by 4. Both of these were in some sense multiplied by 2. The carry here has multiplied by 4. So this number has nothing to do with the second bit of the answer. These two are both multiplied by 2. Correct? This is answer 1. Correct? This is 4. This is 4. This will always be 0. You can check that. Okay. Again, this has nothing to do with quantum. This was just a fun exercise, so that you don't keep sleeping. Cool. That's me. I want to make a quantum circuit. So what do you mean by add? Right? That was the whole point. That is what I want to do. But since I can't do it quantumly, I will do half add. Sorry. Sorry? Which ancillas? You mean?
Maybe can we use just 2 half hours with maybe
You can make a circuit and show me. I will be happy if it can be done with 2 half adders. I don't know. You try it and tell me. Yes, it will be good to know. So I don't know the answer. Okay, good. So this works. Huh? This carry and this carry and what is A1? Oh, this carry and A1. Then you will have to add once again B1 in there before you can say it. Sure, that is fine. So exactly. So the reason why I like this is that the same idea, as I told you, right? So now, once you have the 4 bits, right? Remember, where was the 4? This was the 4. Correct? Now A2, B2. The A2, B2 answer will be the 4. And you will have an 8. So then you will start adding all the 4s. Whatever you get for 8. So this circuit can actually be extended even for 3 plus 3 addition or 4 plus 4 addition. And I'm sure what you are doing can also be done. You just have to keep track of, you should never add a bit which is actually in your answer is getting multiplied by 2 and multiplying by 4. There is no point adding them because that's a mismatch. So you keep track of it and you can make sure that everything works fine. Right? Sounds good? Cool. Okay. So yeah, again, a very good exercise. Try it. Once you get the carry, you add A1 here and you can try to complete the circuit. I'm sure you can. Okay. Okay. So from that answer, you will add B1 again and that would be your answer too. That's completely fine. Huh? Okay.